Yeah. All right. Awesome. All right. Great. So I'm glad you're here. Welcome. Thanks for coming. I'm really looking forward to talking about this. It's a very exciting topic. There's a lot of, I think, fun content for today. I'm looking forward to it. I hope that there is something for everybody. I know there's a lot of diversity in the audience in the sense that some people are just starting their journey in data science. Some people are here with PhDs. Some people are here from industry. Totally lots of different kinds of people. So I'm going to try to hit on some things that, you know, are accessible to everybody. So I couldn't hit my slide advance button. There we go. Okay. So the outline is we're going to start off just making sure, in case there's anybody here who is totally new to the topic of large language models, we'll start out with an introduction. We'll just define the basic terms, and we will also get to together build a very tiny language model here together. And then in the middle section of the talk, that's where we will talk about some of the more advanced content. That's why it's called Going Deeper. And that's the part that's going to be sort of the most technical and the least interactive part. And then we will come back to something I think for everybody at the end, where we're talking about how can we as data analysts use large language models in our day-to-day work, and what are some of the things we might want to be wary of, or some warnings about what might go wrong when doing so. So that's the plan. I do have to confess, I think the schedule said that this is a workshop. I don't know what your definition of workshop is. I thought about how I might run a workshop, and when I think of a workshop, I think of like people getting out their laptops and us like coding something together. But I think there's so many different experiences in the room. There's like some R people and some Python people and some people that just got into this and haven't got past Excel yet. And all of that is fine. And I didn't want to figure out some way to try to bring us all together. So there's going to be interactive stuff happening, but I'm not going to make you get out your laptops. It's going to kind of be more like a talk, and I hope that's okay. Okay, so by way of introduction, let's make sure that we're all on the same page and get some basic terms out of the way. So here are 5 really commonly used like buzzwords and abbreviations in the space of AI, machine learning, large language models. And I have them in these boxes like this on purpose because AI is sort of the broadest term, and then we get more specific as we go down the slide. So let's just think through some examples in each of these categories to make sure that these terms make sense. So artificial intelligence, AI, is the broadest category. That has been around since the 50s. And probably lots of people in this room, when you were kids, did this. If you were Mario at some point in a go-kart driving around, there were probably about 11 other people racing against you, and they were controlled by the computer. And you would say, oh, that's the AI did this, or the AI did that. You refer to that as the sort of, these special little intelligences that can drive a little car around to play against you as a kid in your Nintendo or whatever you had. So that is a correct use of the term AI. That is a little specialized intelligence for one task that was built by people. It doesn't ever learn anything, and it doesn't grow, which is what we tend to think of as AI today, because a lot of the AI we do today is machine learning, a subset of what you would call AI. And in that case, machine learning is when you maybe create a system that can grow and learn from experiences, and then you show it a lot of experiences, and you expect it to develop a skill because of what you've shown it. So for example, you might show it a ton of pictures of cats, labeled cat, and a ton of pictures of dogs, labeled dog, and expect that it will then learn to categorize things in those 2 categories. So that's an example of machine learning. Then generative AI tends to be also a subset of machine learning. And this, of course, is AI that can create content, not merely classify or judge or consume content. There's been a lot of advances in that space with AI-generated art in the past year. And then if we're not talking about generating images, but generating text, that's where we get to large language models, or LLMs. You don't have to use a large language model to generate text. You could use it to consume text and then process it for some other purpose. Like, for example, Google uses an LLM when looking at your search queries to make sure they understand them well. At least they do now. Maybe 3 years ago they didn't, but they do now. And so it's a little bit of a lie to put LLMs as a subset of generative AI, but most of the time they are. And then the most famous example within the LLM category is a GPT model, ChatGPT. Although, of course, there are lots of other models that have, skills comparable to, in some cases, superior to ChatGPT. And these things are sort of, improving and outpacing one another all the time. But throughout this talk, I'm just going to say ChatGPT when I'm referring to a large language model, because it was like the first one to make headlines. So it's the one that comes to everybody's mind when you think of these things. GPT stands for Generative Pre-Trained Transformer. Generative because it's in this category of generative AI, and pre-trained because somebody has prepared the model for you and it's all ready for you to use. And transformer we will define later. I just realized this screen is enormous. I had a couple of times when I was planning on saying, I know you can't read that tiny word over there, but let me tell you what it says, and I will not have to say that at all. Okay, so now those are the terms out of the way, and now I would like to take a look at the way a language model works and make a little one together. So whenever you think about any AI system, it's really good to think in terms of what are the inputs and what are the outputs. Think of it in terms of some code that you might run. You put in some inputs and get some outputs. Or think of it in terms of a mathematical function where you plug in some X value and you get out a Y value, right? And we tend to think of a large language model or a ChatGPT like this, right? Where it's a function where I plug in some prompt text and I get back some response text. But we should actually not look at it that way for the following reason. First of all, how many people here have used ChatGPT? I thought so. Okay. You have probably seen how when you ask it a question, you hit enter, the answer does not just appear, right? It goes as if it like types really fast. That animation is not there for fun. That is really how long it takes the thing to produce each word, and it does produce the words one at a time. So the way you should look at that model is more like this. What you're plugging in at first is your prompt, and well, you're not plugging this in, but the sort of web interface that's talking to the OpenAI server is telling it, you have not yet sent any response to this user. So you get your prompt and an empty output so far. And what it sends back to the web interface that you're looking at is the first word of the answer. Then that web page you're on calls the model again and says, here was their prompt, and here's the one word you've given me so far. And it adds one more word over and over and over really fast. Now, normally, if you had a Python function that you or I wrote and we ran it over and over and over to generate text, it would happen so fast that the answer would be there immediately. But ChatGPT is a really big model, so you can actually see how long it takes for it to make each word, even though it's running on some giant server somewhere. Okay, so in this way, these large language models, at least the GPT models, are not much different than your phone, where it is looking at the text you have just typed, and it is predicting what the next word might be, right? And it's suggesting to you a couple of options above the keyboard there. And if one of them is what you want, you can push that button. Now, it's rare that we would push that button over and over and over, right? It's usually not right that many times in a row. That would be kind of amazing. But if you did, then you would be behaving sort of like the web interface for ChatGPT. And you could use your phone like text generating AI, even though it would be a bad one. Right? Okay. So now I would like us together to make a tiny language model. And it's going to be so tiny that it is only going to look at the last word in order to predict the next word. It's not going to look at the entire prompt or the entire sentence it's seen so far. We're going to make a baby language model that only looks at the last word to predict the next word. Okay, very limited. And let's see, where are we here? So here's what I'd like you to do. If you have any device, you can get at your phone or a laptop or whatever you want, and go to this web address. So that is tinyurl.com/dsd-demo for Data Science Day demo. And you will see there, here, let me show you. Well, I'm not going to take this off so you can find this, so you can keep this URL up there, but I'll show you in a minute. I guess I don't have to show you. You can see it on your own device. It will tell you we're going to use a tiny, tiny language, just 15 words from English. And it will give you those 15 words. And it wants you to write a sentence and submit it into that Google form. So go ahead and do that. You don't have to do this if you don't want to participate. You can send me 5 sentences if you want to, but please make them real sentences of English. Don't send me gibberish because we're training a little AI. Don't be nasty to the AI. Give it real English so it can learn. All right, I'm going to look at my phone because I have up the Google Sheet where all of the stuff you're sending me is going, and I want to see if answers are coming in. Oh, they are. Nice. All right, I'm going to wait. We have 8 sentences, 9, 10. Okay, I'll give you another minute. I'm going to mess with the Zoom here so I can share my screen of some other stuff. Give me one moment while you do that. Oh, if you put in any punctuation or anything, it will just be removed and just your words will be kept. So yeah, you can put whatever, capitalized, lowercase, punctuation, whatever. But if you put in any nasty words, your result will be thrown away. Yeah, you can use words as many times. You can write a tiny sentence or a gigantic sentence, whatever you want. Okay. Let's see how many sentences we got. Oh, lots. You guys did great. Oh my gosh, they keep coming in. Okay, but that's plenty. Thank you. You can stop. Okay. So, how many people have used or heard of Google Colab? Awesome. So this is also not a surprise. For the few folks that did not raise their hand, it is a free online environment that Google provides that lets you run Python code. That's all you need to know for the purposes of this demo. You do not need to be able to read this Python code, although you can if you want to. I will tell you what it does. So this is going to be, we're going to now, in this Colab notebook, we're going to take the data you gave me and we're going to train a tiny language model. And here's how it's going to work. This first cell of code I did not write. This is a boilerplate code from Google that reads from a Google Sheet, specifically the Google Sheet that you just filled with the data you just gave me. All right, so now the way we are going to train this AI, you recall I said it's only going to look at the previous word when predicting the next word. So that means it just needs to pay attention to what words show up next to one another in pairs in the data you gave me. So it's just going to go through all the pairs of words that showed up next to one another and count them. And I just ran this and it did that. And okay, you can't see it in this giant Python dictionary. That's not visible. So we're going to look at it in the table instead. Oh, I got to get the little like zoom thing out of the way here. Okay. So here is a table. On the left-hand side, the row headings down the left-hand side, those are the first word in a pair. And then across the top, the column headings are the second word in a pair. Lots of zeros appear in this table because lots of things you can't say in English, and good job not saying nonsense. So for example, if we look at the top left corner, nobody ever said that. Nobody ever put the word right next to the word Good, thank you. And there's lots of zeros because nobody ever said played the or dog or any weird thing like that. That's great. But you'll notice lots of people said the child, right? 29 times people said the child somewhere in their sentences, all right? And it just counted all those up. So if you wanted to use this table for prediction, you could just pick a row. And when you saw, let's say you were at a point where the previous word was the, so we'd be in the second row of the table, and you would know that child follows the a lot of times, and dog follows child sometimes, and so on. And you could sample a word from the column headings with probabilities proportional to the counts in that row, right? That's how you would randomly generate the next word. Okay, so this code does that. And then here it's been run 10 times. Now, don't expect wonderfulness because it's a tiny model. But let's see, we have the giraffe after a bike. Okay, that's not that great. I can't tell if that's because the model was not so smart or if that's... Okay, the child ran after a dog. Nice. You guys gave me good sentences. It learned the box, period. Okay. The child saw a dog. Great. All right. So you see there's some nonsense and some good stuff. A lot of the nonsense is coming from the fact that it's only looking at the previous word when guessing the next one. So there's sort of like locally like English, but not in the grand scheme of things. And then I'm not going to read that last one. That's crazy. Okay. So the thing that I want us to take away from this, let me go back to, okay, hold on. I have to play with Zoom here for a second. I got to show this, and then I got to switch my Zoom. Where's my Zoom controls now? Here they, oh, hold on a second. Oh, I think Min is going to come help me not get confused about Zoom. Yeah, make it two screen, you know what to do. All right, while he's fixing that, I'm going to ask you, if I wanted to take that tiny baby model we just made and expand it to be more sophisticated, what are some of the limitations that we just saw there that I would need to take away, right? What are some of the limitations of that little model that we would like to fix? And you can just go ahead and like shout out an answer and I'll repeat it into the mic. Limitations of that tiny model. Use more words. We only had 15 words of English. Yes. Homonyms. Oh, tell me more of what you mean. That's one I didn't think of. Oh, yes. Yes, a word can mean more than one thing. Polysemy. But I hadn't even thought of that idea, but I'm glad you reminded me of it. Okay, good. Anything else? Yes, it needs to look back more than just one word. Okay, great. All right, so let's try, I asked you that question prematurely because I wanted to fill time while we were fixing the thing. First, before we get on to what I was just talking about, I want you to notice the pattern in what we just did. So when we think about mathematical modeling, here is sort of the general scheme you can use when thinking about building a mathematical model. You'll have some general model, which is like your plan for how you're going to do this. Then you'll have some data you want to use to shape the model to the situation you're in. You will go through a training procedure to do that, and you will have, in the end, a model that fits the situation you're in. And I know I said training because that's like the way machine learning people talk. Because this is a New England Statistics Symposium, maybe I should have said fitting, but they're not going to come up and take me off with a cane right now. They'll at least wait till the talk is over before they yell at me. So in our particular case, the general model was the plan I had before I came here and you gave me all your data. And that was, I had that 15 by 15 table, but it was empty, all zeros, no frequencies of pairs of words had been counted. Then you gave me all your data in Google Forms. And then the training was really easy. It was just counting how often two words showed up adjacent to one another. And when that was done, we had a filled in 15 by 15 table that we could use to generate sentences. So that's how we built the model. And then the way you would use the model, of course, we already talked about that. But here's an example. If the prompt was the, which it was in every one of the sentences I generated, then you would do what we did. You'd look across the row that starts with the and sample a word in proportion to the counts in that row. And maybe you'd get child, and then you'd have the child as your sentence so far. Plug child back into the model and it would sample a word for you from that row and so on. And you keep doing this until eventually the thing spits out a period, which means the sentence is done, and you print that out, and that's the sentence we generated. All right. Okay. So now you just told me what the limitations of that model were, including make sure we look back more than one word, make sure we use more than 15 words of English, be careful with the fact that words can mean more than one thing. And so if we were to try to make those changes with the extremely simple plan we had here, a frequency table, like the 15 by 15 table, that would very quickly get out of hand. So for example, if we wanted to try to use all the words of English, there's about 150,000 of them in the Oxford English Dictionary. If we wanted to look back only 4 words, well, we'd have like quadruples of words as row headings, and the table would get to be, it would have more entries than there are bytes in the largest data center on Earth, so that's not going to work. And if we wanted to look back maybe 16 words, well, we have more entries in our table than there are particles in the universe. So this whole make a table plan is not going to cut it. We're going to have to do something more sophisticated. Obviously, ChatGPT does not work like this because it can look back way more than 16 words in what you said. So it does something more sophisticated. Let's find out what that is. All right, so this is the part of the talk where If you have coffee, go ahead and sip it, because we are going to very quickly go through what the architecture of ChatGPT is at a high level, because I'm not an expert in this area. And so this is the technical part, and then we will get back to some more like interactive stuff in the third part. But we are still going to stick with this same general plan. It is still going to be a model, a general model that we're going to put data into and train it in some way to produce a trained model that can be used. Okay, let's start at the bottom with the data. Since we're going to make a more sophisticated model, that model is going to have some kind of math happening in it. We're not just going to make a table and look up numbers in a table. There will be some math happening in this mathematical modeling. And you can't do math on words. So we're going to have to turn the words somehow into numbers to be able to go into our model. And now I'm going to ask you a question, so get ready. You could do it like this, right? You could just say, all right, I'll list all the 150,000 words of English in order. And the first one will be word number 0, and the second one will be word number 1, and so on. There we go. I've turned words into numbers. But if you have had a statistics class in which they talked about categorical variables, I'm sure your statistics professor told you, never do this. Why should we not do this? What is bad about that plan? Yeah. Okay, so almost. I'm gonna repeat that answer, and I want somebody to tweak it just a little bit. So the suggestion was maybe there is some relationship, like an ordering here, that really shouldn't be there. And you're close. There is actually, however, an ordering of these words, right? They are actually in alphabetical order. So that actually makes sense. So it's not the ordering, but what other relationships are wrong, wrongly introduced by these numbers? Yeah, Jonathan. Right, we are not going to do computations on the words. It is not the case that 3 times aardvark equals a back, but it totally looks like that based on these numbers, right? And even more, just what's near to what, even when we don't do math, is potentially a problem. You might get some happy coincidences, like, for example, those two 300 and something numbers are close to one another, and hey, great, assist has a similar meaning to assistance. What a happy coincidence. But that doesn't always happen. Like, these two 5,000 something numbers are close to one another, but those two words are totally unrelated. In fact, Malays means, oh, I don't want to do anything, and Malagueña means, I would like to dance. So they are totally opposites, actually. So you would not want the math to not reflect the meaning of the words. In fact, to contradict the meaning of the words. That would be a bad encoding of the data. Now, there are people who have developed very sophisticated encodings of the data. These are called word embeddings. The pictures I'm showing you here come from a Financial Times blog post by their data storytelling team visual storytelling team that I highly recommend. The link is on the bottom of the slides. These slides should be available on the NES Data Science Day website. Yes? On Whova. Awesome. Okay. So all of the links that you see in tiny font on the bottom, if you want to know more about any of the slides, just grab the slides later and follow the links in the bottom. They take you to academic papers, YouTube videos, blog posts, all sorts of stuff. So I'm not going to go into how word embeddings work, because I'm going to let you see how they work on the Financial Times website. But I will just say you should think of words as points in space. This visualization on the right-hand side uses just 2 dimensions. That's drastic oversimplification. It's in hundreds of dimensions, but just for our own human intuition, you can think of every word as a point in space represented by some vector of numbers. Okay, so that word swim, maybe that's a word we care about, and it's at this location in space. So for the rest of this talk, I'm going to assume that a word is a vector of numbers. And you actually have to also encode in that vector somehow the position of the word in the sentence, but that's not important for this talk. Okay. So once we have our words as vectors, we know how our data is going to be presented to the model. But the interesting part is, what's the model going to do? So let's do that next. Now, when I switch to the next slide, there's going to be a sentence on it that I want you to read in your own mind silently. And you will see in that sentence, there are 2 underlined words. The same word appears twice, underlined. And it means something different the first time it appears than the second time it appears. And I want you to pay attention to what your brain does. How do you, as a human being with a brain that understands language, tell the difference between these 2 occurrences of the same word? Okay? And then after you've read the sentence, you tell me what your brain did. Okay. How did your brain tell the difference between interest in one sense of the word and interest in the other sense of the word, as we heard earlier, we would need to do? Just anybody who has, I know it's a little weird in a room of like 90 people to tell everybody how your brain works, but I'm asking you to do that. Yeah. Okay. The word rate comes after interest, and that really clues you in the second one that that's one kind of interest and not the other one. Yes. Okay. And thank you. And in general, the idea is what words surround the word make a big difference in how we interpret the word. So I said we were going to encode words as just vectors of numbers, but that's how you would encode the word by itself. We want to somehow treat words based on what's surrounding them that clues us in to what the word means. Okay, so this is a problem called attention, and it is the central invention of the past decade that makes large language models possible. And it's the idea that the computer needs to do what your brain and my brain do when we look at words. We need to look at the words nearby and figure out which ones do we have to pay attention to and how much. So this question, when I'm focusing on word X, how much attention do I need to pay to each surrounding word Y? So like, for example, with that top word interest, maybe I'd look at the words nearby and I'd say, oh, that word no, that's not very helpful to me. I'm going to give that a low rating, like 10%. Oh, but interest in hearing. Oh, interest in hearing, that means the human kind of interest. Hearing was a really important word. I give that a high rating. Okay. And I'm just rating them on a scale of like 0 to 100 here, like percentages. But then on the bottom row, it's like you were just saying, maybe rising doesn't really help me very much, but interest rate, oh, that helps me a ton. Understand that word. Oh, and bank at the end of the sentence, that helps. But from those were not very important. I gave them a 0. Okay. So we want to somehow come up with a way to do this computation of when I look at a focus word, how important are the surrounding words? How much attention do I need to pay to them? All right, so I want to lift out just that first phrase, no interest in hearing, because we're going to use that as an example when we go through. Well, I'm going to show you a very complicated flowchart of how ChatGPT works internally, and we need a little example to help us navigate that complicated flowchart. All right, so we're going to have no interest in hearing, and these weights, and we're going to call those word 1, word 2, word 3, and word 4. All right, so just keep this example in your mind. So this flowchart is going to go from left to right, and it's going to be, like an abstract representation of a computation. So the input words come in on the left. You could have n of them. In our example, we have 4. And we're going to pick one of them that is the focus word that we're trying to interpret. And then all the other ones are these surrounding words, and we need to figure out, okay, how important are they? And so somehow, and I haven't said how yet, we're going to be assigning an attention weight to each of these surrounding words. And we had used as an example, the 0.10, the 0.30, and the 0.85 were the example. But once we compute that information, here's what we're going to do with it. We're going to use those weights to somehow mix in the meanings of the surrounding word into the focus word. So we're going to change the word vector for the focus word to contain a little bit of the meaning of each surrounding word. And when I say a little bit, I mean in proportion to how important it is based on, how important we've judged it to be with this computation up top. Okay, now, the two really important things that I haven't yet explained are how do we compute those attention weights? And then how do we mix in the meanings of surrounding words to the main word? But before we talk about that, I know I keep putting off the interesting thing. Before we talk about that, I want you to point out that these 3 arrows on the left are actually a problem in this plan. You'll notice we've got word vectors coming in on the left. They're just vectors of numbers. Nothing special there. But I'm expecting those vectors of numbers to play 3 different roles. On the one hand, any one of them could be selected out to be the focus word, and that's one job those vectors have to do. And on the other hand, all of them are going to sometimes play the role of the surrounding words. That's a totally different job those word vectors have to do. And then somehow I'm going to use them as like meanings that get mixed into their nearby words. That's a third job I'm expecting them to do. That's just too much to expect of one simple vector. That's too many jobs for it to do. So here's what we're going to do. We're going to introduce some mathematical functions to solve that problem. I'm going to make a function f And its job is to convert a plain old ordinary word vector into one that can play the role of the focus word. Then I'm going to create a separate function S that will take the same input vector, but now prepare it to play the role of a supporting word. So I'm no longer expecting that input vector to play two different roles. I'm going to convert it so it's ready in each case to do a different job. Finally, I'm also going to create a function M that takes any one of those word vectors and prepares it for the third job it might have to do, to be a meaning that you could mix into a nearby word. Okay, so now let's answer the question finally of how do we compute the attention weights. Here's the crazy thing. We're going to do it just by doing a simple dot product of the focus word with each surrounding word. If you have not had a linear algebra class and you're going, what, dot product? What is that? It's just a weighted average of the two vectors. That's all it is. Now that sounds a little bit crazy because I just said that the really hard computation is just a dot product. Hold that thought. Also, this complex operation down here of mixing in the meaning of surrounding words into the main word, that's also going to be just a simple weighted average. I'm going to take the weights that we compute up there, and I'm going to put them out in the front of each of the outputs of the M function, add them all up, and add them to my focus word, and that's the new value of the focus word. So now, how can this be the case? How can it be that this thing I said was a really complex computation is just some like adding and multiplying? And this thing that I said down here is a really complex computation is just some adding and multiplying. The only way that can make any sense is if all the hard work is being done by those three functions. So really, I've sort of just like swept the story under the rug here, and I haven't like told you anything. I've just said, oh yeah, we're going to do something complicated over there. And I haven't said what it is yet. Well, the surprising story is that I'm not going to tell you how to build those functions either. Nobody builds those functions. All you do is put a neural network in each place and expect the neural network to figure out how to build that function itself. This is part of the sort of amazing flexibility of neural networks, is that like wherever you put them, they figure out what they're supposed to do. So the invention here of this flowchart is not really so much devising clever ways to model language. It's rather just structuring the problem in such a way that you can put neural networks into the places we need them to do, these three jobs of figuring out how do I prepare a word to be a focus word? How do I prepare it to be a surrounding word? How do I prepare it to be a meaning I can mix in? And then they'll figure that out. So you just like create room for neural networks to do what you want, and they do. So this whole flowchart here is assuming we're focusing on just one word, W2. So I'm going to reframe it because, of course, you have to do this for every word, not just one of them. So to summarize at a high level, we take our input words, we send them through one neural network to get each of them ready to play the role of the focus word. We send them through a second neural network to get each of them ready to play the role of the context words. And then we consider all the possible combinations of those, every focus word compared to every context word. And we just take a dot product to find these attention weights. There'll be a little table of n by n weights. Then we send all of the input words through a third neural network to get them ready to be meanings you could mix in with their neighbors. And then we multiply them by those weights and add them to their neighbors to take their meanings and mix them into each of the individual words in the sentence. So the n words that came in, we now have converted versions of every one of them that I'm calling word 1 prime through word n prime. And they're the same words that we started with, except each one of them has a little bit of its neighbors mixed in some way that through the training of this network works. This scheme right here, this flowchart, is called, so this is the attempt to make a computer that does what you told me your brain does when you look at this. Right? And that is called an attention head. That is what that network structure is called. Now, I know that I didn't tell you anything about how neural networks work today. You just have to believe me that they're really flexible things. But if you would like to see more about how neural networks work, there's a link there to a talk I gave about how neural networks work. You can follow that. And if you want to know more about this concept of attention, the seminal paper that introduced this idea as the key ingredient to large language models is linked to down there. That's one of the two main new discoveries that I wanted to tell you about today. That's from the title slide. I told you I would tell you about some new discoveries in large language models. The title of that paper is "Attention is All You Need." It's from 2017. And it says, if you build a large language model just by repeating the structure on this slide over and over, it will work great. Right? So here's how you do that. We can make a simple picture of it, actually. Imagine the user's prompt coming in. We're going to send that user's prompt to a whole lot of copies of what you just saw on the previous slide, the attention head. Lots of them. I've got 4 here as an example, but you'd send it to lots of them. Each of them can specialize in a different type of attention. So, for example, maybe the first one would specialize in how adjectives relate to nouns, and the next one would specialize in how the subject of a sentence relates to the main verb, and so on. Whatever each one of those wants to learn independently of the others, it can. Then we will collect all that information together using some other neural network. And each of these neural networks is sort of a plain vanilla one, like just a couple of layers densely connected or something. It doesn't have to be sophisticated. Then the machine also needs to pay attention to anything it has printed out so far. So we will take any output that has come back out of the model so far, and we will run it through the exact same system so that it can read not only what you asked, but also what it has said so far. And then to bring all that together, you guessed it, we do the same thing again. And that structure will allow us to then predict the next word. This architecture is called a transformer architecture, which is the T in GPT. Generative pre-trained transformer means the inside of ChatGPT looks like that. Okay, that was slightly a lie. This part here, you can repeat as many times as you want to make the thing really big and to give it the capacity for higher level thinking. But basically this structure with that box repeated many times. Okay, that was the hard part. So we said earlier that our data would be word vectors, and now we know that the model is going to be a transformer. The training procedure for any neural network-based model is called stochastic gradient descent. We don't have time to talk about that, but if you would like to learn more about it, I'll give you a link to that in a second. And now we no longer have here the general structure for a mathematical model. This is the structure of a large language model. There are 2 links down there. One of them is to a free course that MIT put online in January that'll tell you all about neural networks and how to train them. I'm halfway through that course and it looks really good so far. I highly recommend that. Well, I highly recommend the first half. I suspect the second half is good, but I haven't got there yet. And the second link is to the other new discovery that I wanted to tell you about. It's from a paper just a year ago. Actually, no, it's to a blog post that covers a paper a year ago. And it's about how large is large. And the idea is there are strong relationships between how big the model is and how much data you have and how many computing resources you can afford to spend in training it. And they're starting to discover the most efficient way to decide the size of your model. But that's, that's a very recent innovation. Okay. We are now coming to the third and final part of this, and I'm going to expect your participation again. So I want to talk about ways to use large language models in your day-to-day data work. I want to tell you 3 ways you can use it and 3 things to be wary of. I'm not going to tell you should go to ChatGPT and ask it to write some code for you because everybody knows that. I'm going to tell you 3 other things. So the first one is that you should get some AI that is watching while you code and suggesting what you might want to type next. And the reason I suggest that is because, and I'm calling those co-pilots because the famous one is GitHub Copilot, and then lots of other ones were invented also. Some of these are paid products and some of them are free. And the reason I suggest that is because there is an overhead involved in deciding you need help, switching over to a large language model like, whether it's ChatGPT or Bard or whatever, Codex, and formulating what you need in the form of a precise question, hitting enter, reading what it said and deciding if it's right, maybe changing your prompt, et cetera, until you get what you want, copy, paste it back where you came from, tweak it to fit your situation. There's a lot of overhead in that. But if the thing is just watching you code, sometimes you're like, I've had the experience where I write a comment that's describing the function I'm going to write. And when I hit enter, it writes the function. And I'm like, yeah, that was the one I was going to write. Thank you. And I just hit tab and move on. So it's pretty amazing. And it really saves you that turnaround time of having to go over to the model and ask it a question. It just figures out what you want to do. So that's the first thing I recommend. The second thing I want to suggest that is, I don't know if this is something that these models can do or not. They can extract features from text. So for example, here's a prompt that I gave to ChatGPT just to test this capability. I found a story on the internet, which is about somebody's childhood. They were reminiscing about their childhood in elementary school. So I wrote this. Please read the story I've included below and respond with a JSON data structure of the following form. If you're not familiar with a JSON data structure, it's like a Python dictionary. I hope that helps. It looks like this. Name. Put here the author's name if they gave one or leave blank. Mother. Summarize here any comments about their mother because it was a childhood story. Other adults, same thing. And then I said, now here is the story you should analyze as described above. And I pasted the story and it was one big prompt and I ran it. And it did exactly what I asked. Not quite. I told it to leave name blank and instead it said no author's name provided. But basically it did what I asked. And you could imagine asking for a structure that had many more than 3 entries, right? You could imagine that if you had a lot of text data that you needed to extract features from, maybe you wanted to do some sentiment analysis. Maybe you wanted to just ask for the names of the characters in the story or anything, that you could automate that process with a cleverly devised prompt that you stick a story after, right? And then you might imagine that if you had to do that for 1,000 pieces of text, you would want to automate that. And that's the third thing I want to tell you is that you can automate that. You can call ChatGPT from your own code. There is a Python module for this purpose. There's probably an R module for it too. I don't know. I teach the Python class. And it is just literally this much code to give you the function you need to call ChatGPT from your own code. Where I got this code from is the link at the bottom there. It's a free online course that takes you 1 or 2 hours to go through. It's run by engineers from OpenAI and Deep Learning AI. And not only does it tell you how to use this code, but it also coaches you through how to develop prompt templates that you can use to make sure that your queries to the AI bring back the kind of data that you want in the format that you want it. So you could imagine taking a whole lot of text, a whole lot of qualitative data, and extracting from it a lot of features that are of interest to you and building a data table out of them using something like this in a loop. So lots of potential for tools like this in your data work. So what's the catch? All right, so this is the last thing that I want to talk about, and that is how to be careful when using tools like this. So the first thing that I want to point out is that, we talked about this structure of mathematical models and large language models. And when we came to the data part, I just said, yeah, we're going to make it into vectors. Great, let's go. I didn't talk about where the data comes from. And it's worth noting that right now, when somebody trains a large language model, they tend to grab as much of the internet as they can get their hands on. A really large portion of the internet is written in English, and therefore it expresses the opinions of and talks using the style of and includes the ways of thinking of people who tend to speak English. So the first thing to remember when you are using these models is that they were trained on data that does not represent all humans on Earth equally, and therefore they will give output that does not represent all humans on Earth equally. So that is the first warning, is that the model leans toward favoring certain people and not others. All right, now this is where I want some interactivity from you again. So some researchers from Purdue University did a study where they took questions from the tech website Stack Overflow, question and answer, and they gave those same questions to ChatGPT, and then they graded its correctness, how well it did. And then they also showed the responses to real people and said, do you like this answer or better or this answer? And they sometimes showed them a pair of Stack Overflow answer written by a person and the ChatGPT generated answer to see how often people liked the one versus the other. All right, so we're gonna do a show of hands. You're gonna vote for what number I'm going to reveal under that top blue square of how often ChatGPT got these tech questions correct. Your 3 votes, your 3 choices are gonna be way less than 25%. I'm sorry, way less than 50%, like roughly 25%, roughly in the ballpark of 50%, or way more than 50%, like in the ballpark of 75%. Okay, so you have to vote small, medium, or large. So you are voting on the correctness rate of ChatGPT. All right, how many people vote and think that it got way less than 50% of them correct? Okay, this is a confident room that believes our future with AI is going to be wonderful. How many people believe it is about 50%? That looks like a little over half of you, maybe 3/4 of you. And then how many people believe that it was way more than 50%? Okay, yeah, just like a dozen people or less. Okay. Okay, so the majority of you were correct. Good job. It was correct just under 50% of the time. Now, then people preferred the ChatGPT answer about 40% of the time, which raises the question, how do those two sets overlap? Were people really good at distinguishing when it was right and they liked that answer, or were they not? They were not. People liked the ChatGPT answer in a way that actually really disproportionately picked the bad answers. And so why did they like it? Well, they tell you why. These are the results from the study. They love the answers because they're comprehensive and thorough and articulate, confident, polite. They sound like a textbook. It sounds so convincing superficially. In fact, this is what it was designed to do. This image comes from OpenAI's blog about how they built the thing. And I'm not going to go through, obviously, this whole flowchart. But in step one, they had human experts write answers to prompts. And then they showed a lot of those to the model and said, talk like these people. And then in phase two, they showed a lot of output from the model to real people and said, tell us which versions of this answer you like better. So in other words, one part of it was teaching the model to sound like human experts, not to be right, just to sound like an expert. And in part two, people, tell us what you want to hear so we can make the model sound like what you want to hear. So it should be no surprise whatsoever that it sounds like what we want to hear and it sounds like an expert. However, putting that together with the fact that it is not so good at answering tech questions, less than 50% of the time correct, that's a little worrying. So when you get answers from ChatGPT, check them. Okay, so those don't count as three things because those middle bullet points came from one thing. The last thing I want to tell you is this one. So if you ask ChatGPT what it's not allowed to talk about, it will give you a long list of things. It's not allowed to talk about violent things or sexual things or self-harm or a whole long list of things that it's good that it's not allowed to talk about. I asked it what it's not allowed to talk about, and it told me this list. And it goes on and on off the screen. Okay, this is now the last interactive part. Here's how we are going to play this game. I'm going to tell you a hypothetical story, and you're going to have a role to play in the imaginary story. And if at any point you are bothered by the ethics of the situation you're in, I want you to put your hand up. Like, I would object to that. I don't like that. So your hand goes up if you don't like what's going on and you would, refuse to participate, and your hand stays down if you're fine with the situation. Okay? So there's no not voting. You're voting with your hand down by saying, yeah, I'm fine with that. Okay? Okay, here's the story. So you run a small data company, and OpenAI comes to you and says, we built this large language model and we would like to make it safe. We need it to be able to recognize all of these harmful categories so that it won't participate in them. Consequently, we need a whole bunch of data categorized into all these harmful categories or the safe category so we can train our model to notice when it's in the harmful categories and which one it's in. Consequently, we're going to hand you a whole ton of data, some of which is safe and some of which is in all of these harmful categories. And we need you to hire some people to look at that and categorize it into those categories. So they will need to pay attention to this data enough to categorize it into the categories. And so will you please hire those people, and 40 hours a week, they're going to look at this content and categorize it for us. Nobody's hand is up yet. Okay. Okay. Somebody with their hands up already. That's good. Okay. Now imagine that you are doing this in a country in which people are desperate for work. Does that make you feel better about it because you would be glad to give those people money, or worse about it because those people are going to do things that are bad for them because they're desperate? I see some hands are up over there. Okay, great. You just keep your hand up if you don't like what's going on, and you might pull it down if the story changes. So like, for example, maybe your company says, okay, we are going to offer free mental health counseling for all of our employees for anything at any time. And we're going to do a wellness check every day they arrive at work so that they don't go into perceiving this content if they are not mentally healthy for that day. Okay. Then imagine that while let's then imagine that you proceed and you take this contract, and that the employees are showing up for work, and even those that are passing the mental health check for each day, their personalities are changing, some of them so dramatically that their spouses leave them. More hands are going up. Now imagine that the people that are working for you are vocal about the fact that they are proud of the work that they are doing, making the internet safe for other people. Now imagine that even after all the work is done and turned in, there are still loopholes in the model that will make it talk about things it's not supposed to talk about. All right, that's the end of the hypothetical. You can put your hands down, and it is totally not a hypothetical. All of that happened. And you can hear about it if you go and see this interview on the Wall Street Journal site. The link is on the bottom left. So the thing that I want to leave you with is that even though tools like ChatGPT are free for you and I to use, nothing is built without a cost, and sometimes a significant human cost. All right. Thank you.
Everyone, at this point, we will take questions from the audience. Do we have any questions? All right, while you're deciding on questions, I'm going to check, is there any questions online?
Just go ahead, I can just repeat it.
The question is just regarding like the training process and more of like a traditional sense. If it's say like classification and it's like supervised, you can easily compare what the model is predicting and then compare it to like the truthhood. But when the model is predicting words, there's technically like an infinite number of correct responses. So there is no correct response to compare it to. So how exactly does it update its weights from that?
Yeah, that's a great question. So I can sort of give you a half answer because I mean, I have myself not built a large language model from scratch, so like I don't know every detail, but the output from the model is actually like, let's pretend that we're using a model that can speak the 150,000 words in the Oxford English Dictionary. That's not really how the models work, but that's a good like approximation. So there will actually be coming out of the model 150,000 outputs, each of them a probability that shows a distribution of the words, a lot like one of the rows in our table from the tiny model. And so what you actually are looking for is for the is for that probability distribution to converge to what it would be in the context of whatever prompt was just given in whatever data we have. So it's not like there's one right answer to the word that comes out. It's we want to get a probability distribution that's like what we've seen in the data.
Okay, see, thank you.
Yeah, I kind of made it seem like there was one answer because I just had one output in my slide, but it was just a flow chart. So yeah.
Really getting my steps in today.
It's a big room.
Thank you for sharing. I really enjoyed it. I was wondering that study that you presented where the numbers were like 48% and then also 77%. When was that collected, that study? And then also, where did that come from? I asked because, when it became mainstream, the data set that it was trained off of was up till 2021 data. And then now it's connected to the internet. It has up-to-date data. So I'm wondering if that was beforehand or afterwards.
Yeah, that's a great question. So first of all, these models like change all the time, and some other models are better at answering coding questions than ChatGPT is because it's sort of a general purpose one. The slide that reported that has a link at the bottom to the study that was done by people at Purdue University. Exactly what month of this year that was done in, I don't know. It had to be this year because ChatGPT came out this year, but I don't know exactly when. Certainly, I think the ability for ChatGPT to connect to the internet was just this month, so I don't think it was after that. I think it was a couple months ago, but I don't have the details. You'd have to check in the paper on the slide.
I just have a very simple question that's related to basically like education. Like since the invention of ChatGPT, do you find like a lot of students actually using ChatGPT for their homework or exams or stuff like that, which may prevent their critical thinking development from them?
Yeah, so obviously, it's a huge, concern for educators to figure out, okay, am I giving assignments that people can just do without thinking because the AI does it for them? In my case, I teach a lot of data science courses, and so I actually tell my students to use AI. and then I tell them, tell me when you did, because I want to learn what it's telling you. So like when you turn in a homework to me, it's totally fine if you used AI. I want you, but tell me that you did so, and tell me if you had to tweak its answer or not, because that helps me learn about how the thing works. Now, then of course I have to try to design projects in such a way that there's still plenty of intelligent work that they need to do, even if they use AI. So yeah, you have to be more creative than you used to, but it's, I mean, speaking as somebody who teaches data stuff, it's a little bit easier for me, but it's going to be something that anybody who goes into this career uses at their desk every day. So it doesn't make any sense for me to tell my students don't use it, and then I'm training you for a job that's not what you're going to do, right? I mean, if you if you decide I'm not going to use AI in my job, well, then somebody else is going to be a lot more productive than you. So don't make that decision.
So I will do a rare chime in and say that my students told me that they discern between things. So some things they'll use it for, but other things they'll say, I know ChatGPT is not good at that. I'm not going to ask it to do that. So I think there's already a critical thinking happening there.
I was just going to add a data point to that. So I'm teaching abstract algebra, which is pure mathematics course. And in the first week of class, we did some experiments where we took homework problems in abstract algebra and typed them into ChatGPT. And it's just like the examples here. It produces absolutely convincing proofs, nicely typeset in LaTeX, 50-50 whether they're right. It's better at some things than others, but it's a total crapshoot. And sometimes it's just complete nonsense. Grammatical, but nonsense.
And also, I should add to that that the state of the art, I mean, it's a super exciting time to be in like machine learning and AI, because the state of the art changes like every couple of weeks. Like my Google News feed every week is telling me, okay, somebody else has invented this thing that makes large language models do this. And it like changes all the time. You know, there are people that have invented things that you can add to a large language model that does fact checking and then turns back to the model automatically and updates the prompt and says, you know, that's wrong. You have to say this. And you can sort of add that to the model and then get more reliable results out. And there's people trying to improve those things, you know, so there's, you know, it's changing all the time. Like some of the things that if I gave answers or opinions on these things, they may be wrong by now, you know, because I haven't read the latest thing. So.
Hi, I was just curious, where do you think, where do you see like things like ChatGPT like going in the future? Like how advanced or what purposes do you think they're going to do in our daily lives?
Yeah, I mean, if I knew the answer to that, I would be on a yacht somewhere. And so what the things that are happening now and are in, you know, like in beta releases and things, are the ability to provide more types of inputs and to expect more types of outputs. So for example, you might want to give it, you know, prompt together with some data, together with some images, together with whatever, and ask a complex question about the relationship of all those things. And you might want to get out not just text or an image. You might want to get out, you know, a video or a three-dimensional scene or a composition of music, or, you know, and things that relate to one another. Maybe, you know, obviously something that one of my kids, I know what they would love to do is write a 6-page essay about the video game they want and have it make it, right? So, you know, the greater complexity of the kinds of things that it can create consistently and coherently is what everybody's trying to do. And I think, you know, we're, you know, what, 18 months into this phase of human life, right? So we're going to see 5 years from now, what kinds of things can it build? I don't know. I don't want to make people late to the next thing. Is 3 o'clock? I'll stay here as long as you want me to, but I don't want to be messing something up.
So I believe we have a 15-minute break.
Oh.
So if there's more questions, I think we can fit at least one more question in.
I can talk about this all day.
Sorry, just another question. So I read an article that like these LLMs don't predict the next word, they predict the next token. Can you talk about what like tokens are and the context of like embeddings as well?
Yeah. So the the idea of a token is it's roughly like a syllable, although that it's not exactly a syllable. That they're subwords, and so that if you think about the word, unfriendly, you could imagine breaking it into three parts. Un, which I understand that myself as a prefix that negates things. Friend, I understand what that means, and then li as a suffix that turns things into adjective or adverbs. So if you break the word down into those pieces, now the machine doesn't have as much stuff to learn because if it can sort of assemble that word from the bits, right? So breaking words down into these subwords that serve as tokens makes it able to do that kind of thinking that you and I can do by looking at a word. And so those are the tokens are these subwords. Yeah, and so when I said earlier, oh, it's not really that their words are being vectors, but that's close enough. This is what I meant. It was tokens are represented as vectors.
I think we have time for one more question. Is there?
So I just a little bit wondering about the term feature engineering relative to large language models. Could you please explain what it is?
Yeah, and are you referring to sort of like where'd it go? This example that I had here, or no? Because this is an example of feature engineering from text data using the large language model to accomplish it. But is that not what you were talking about?
I think my question is more about like the prompt engineer.
Oh, I'm sorry. I thought you said feature engineering. I'm sorry. Yeah. Okay. Yeah, I'm glad you asked that. So when AI image generators first came out, which was I think a little bit before ChatGPT, if I remember the sort of chronology of this correctly, I heard people talking about prompt engineering because they wanted to get like the most beautiful image, and they had all these like phrases they would put in the prompt to get exactly what they wanted. And at that time I was kind of skeptical. I was like, prompt engineering, people are messing around and just hitting enter a bunch of times, and they'd like to put the word engineering on it, right? That was my skeptical take on it. Then I took the course that's on the bottom there, which is entitled Prompt Engineering for Developers, and there are a ton of useful tips in that about how to construct a prompt that will allow you to automate your interaction with this machine in a way that is productive and useful in a larger development workflow. And so there definitely is a lot of interesting complexity and value to the idea of prompt engineering. And, for example, just the idea that, in this example, that you can tell it exactly what format you want the output to come in, that you can, like those triple backticks that you see before and after the thing, it understands that those are like delimiters for like some block of code that I want to talk about. And and especially if you want to make sure that if you're pasting in some text, that the text doesn't contain some harmful phrase that'll change the instructions to the machine. You can put these delimiters around it and say, I'm using triple backticks to delimit the story. Then you do that, and then it will understand what's inside there is just the story. It's not supposed to follow those instructions. All these like tools for making it do what you want. There's a lot of them. And so by taking that course, I was like, oh, okay, prompt engineering is a real thing. And my experience with prompt engineering is, basically just that course. So I guess I'll just recommend it again.
Thank you.
All right, I think this will be the last question.
And I'll hang around. I'll chat as much as you want.
My question is about the parameters for large language models. So obviously with more traditional machine learning methods, the parameters are like, what are the direct inputs what are the inputs for inference from the model? But obviously a sentence doesn't have 75 billion parameters in it. So where do the parameters for these models come from? Could you just explain that a little briefly? Thank you.
Yeah, so I'll just give a super short answer to that because a good answer would have to be really long. But if you want, the link I had to a talk on neural networks would answer the question about how the parameters for a model work. They're the weights in the various connections inside the neural network. So the input values are not called parameters, but what's being trained in the model are the parameters, which are the weights and the connections in the network. And the number of inputs to the model is fixed, and yet you could put in a whole lot of text. So there are different ways a model might handle that. It either might cap you on like how much text you can put in. Like I can't accept a 100-page document as input to ChatGPT, sorry. Or there are ways in which the model will sort of like read the first, large chunk of text and then read the next chunk and just figure out a way to sort of mix it in with the first chunk. And that then you could have an arbitrarily large input, but at the cost of some loss of accuracy in some way, yeah.
Thank you. And everyone join me in thanking Dr. Carter for a wonderful presentation.